You think you understand gravity? Step onto a scale. Look at the number staring back at you. That's your weight. Earth pulling you downward. Simple. Drop an object. It falls. The moon circles the Earth. Planets loop around the sun. Anything with mass attracts anything else with mass. Newton explained it centuries ago. Gravity, a force. Clean, elegant, easy to accept, and completely wrong. Not slightly wrong. Not missing a detail. Wrong at the deepest possible level. Because gravity isn't a force at all. And once you truly see what gravity really is, once it finally clicks, the universe stops looking familiar. Everything changes. So let's slow down. Stand up for a moment. Feel your weight. What do you actually feel? You might say gravity, the Earth pulling you downward. But pay attention to the sensation itself. Your feet pressing into the floor pushing back, upward. That's the feeling. Pressure, resistance, a push. That invisible downward pull everyone talks about. You never feel it. Not once. You only ever feel the ground pushing you up. Always pushing, never pulling. So where is this so-called pull? Now here's something even stranger. The moon is falling toward Earth right now. It has been falling for billions of years. Yet it never gets any closer. It just keeps circling, forever falling, never landing. What kind of force behaves like that? A pull that never finishes pulling. And in Newton's universe, it gets even weirder. That pull is instant. Move the Earth, and the moon responds immediately, across nearly 250,000 miles of empty space. No delay, no signal, no carrier. How does the moon know? What delivers the message? Newton himself couldn't answer that. He admitted it openly. He called it action at a distance and moved on. The equations worked beautifully. The predictions were flawless. And because the math was right, people stopped asking the uncomfortable questions. But maybe they shouldn't have. They never should have stopped. Because if you rewind a few centuries, no one actually knew how the planets moved. Copernicus said the sun sits at the center and the planets go around it. Okay, but how do they move? What shapes do their paths trace through space? To answer that, Tycho Brahe did something no one else was willing to do. He didn't guess. He didn't philosophize. He built an observatory. For decades, night after night, year after year, he tracked the planets across the sky. He measured their positions with enormous brass instruments, recording angles with astonishing precision, down to tiny fractions of a degree. Why go to such extremes? Because nature doesn't reveal itself to opinions. It reveals itself to measurements. You have to watch carefully. Record everything. Write down exactly what the universe shows you. That's where real science begins. After Tycho's death, his mountain of data landed in the hands of Johannes Kepler. Kepler wanted one thing: the true shape of planetary orbits. He started with circles. They almost worked. But Mars refused to cooperate. The predictions missed the real position by 8 arc minutes, about 8/60ths of a degree. Most people would have ignored it, blamed the instruments, called it noise. Kepler didn't. He trusted Tycho's measurements. A man that precise doesn't miss by 8 arc minutes. So Kepler did something radical. He threw away his idea and began again. Years later, the answer emerged. Ellipses. Planets don't move in perfect circles. They travel along stretched loops, with the sun sitting at one focus. When Kepler plugged ellipses into the equations, the data snapped into place. Exact, flawless, beautiful. But the solution created a deeper mystery. Why ellipses? At the same time, Galileo was asking a different question on Earth. He rolled balls down ramps. It sounds simple, almost childish, but the results were revolutionary. A ball rolling downhill speeds up. Let it reach a flat surface, and it keeps moving. It doesn't stop right away. Now imagine removing friction completely. What happens? The ball never stops. Same speed, same direction, forever. This idea unsettled people. Surely motion needs a constant push. Surely objects naturally come to rest. But that intuition was wrong. Motion is the natural state. An object moving in a straight line needs no explanation at all. That's the default. What demands explanation isn't motion, it's change. When motion slows, that's friction at work. When speed increases, something is pushing. When direction changes, a sideways influence is acting. This is inertia, the first law of motion. And it leads straight to a problem. If nothing interferes, objects move in straight lines. That's their natural behavior. So planets should travel straight through space. But they don't. Their paths constantly curve, bending inward toward the sun. That means something is redirecting them every single moment. What is it? Isaac Newton saw the pattern. Left alone, planets would move straight ahead. That's inertia, but they curve. So something must be altering their motion continuously. He named that influence gravity, a universal attraction. Every mass pulls on every other mass. The strength of that attraction depends on two things: how massive the objects are and how far apart they sit. More mass, stronger pull. More distance, weaker effect. And the weakening follows a precise rule: double the distance, and the force drops to 1/4. The inverse square law. With that single idea, the chaos snapped into order. Why ellipses? Because planets are falling toward the sun while racing sideways through space at the same time. Forward motion plus inward fall creates curved paths. Ellipses are the result. Kepler's laws weren't replaced, they were explained. They emerge naturally when Newton's gravity is combined with inertia. And the same logic answers another question. Why does the moon circle the Earth? The same rule applies everywhere. The moon is falling toward Earth, but it's moving sideways fast enough to keep missing. So it doesn't crash. It loops. It falls around the Earth instead of straight into it. An apple follows the same logic. Earth pulls it inward. Same law. Same interaction. Just on a much smaller scale. Newton proved this with a stunning calculation. He worked out how far the moon drops each second, how much its path curves away from a straight line as it moves through space. Then he calculated how fast objects fall near Earth's surface. When he adjusted for distance, the numbers aligned perfectly. It was astonishing. The force tugging an apple from a tree is the very same force keeping the moon locked in orbit. The physics of the heavens and the physics of the ground beneath your feet turned out to be identical. With Newton's gravity, the universe suddenly made sense. The ocean tides rise and fall because the moon pulls on Earth's water. Earth isn't a perfect sphere, it bulges at the equator because it spins. Comets return on schedule because they trace long, stretched ellipses through space. Mysteries began to dissolve. Jupiter's moon sometimes appeared early, sometimes late. The explanation wasn't gravity at all, it was light. Light takes time to travel. When Earth is farther from Jupiter, the light has a longer journey to make. Those tiny delays became the first measurement of the speed of light. Planets also wobble slightly in their paths, pulled not only by the sun, but by each other. That wobble in Uranus's orbit led astronomers to predict an unseen planet. They pointed their telescopes and found Neptune exactly where the math said it would be. For nearly 200 years, Newton's law of gravity stood as one of the greatest triumphs in human thought. It explained everything anyone could measure. Almost everything. There was one detail that refused to fit. Drop a hammer and a feather in a vacuum. No air. No resistance. They hit the ground at the same moment. That's strange. The hammer has far more mass. Newton's gravity should pull it much harder. But the hammer also has far more inertia. It resists being accelerated much more strongly. Two enormous effects, perfectly canceling each other out. Those two effects cancel with absolute precision. Not almost. Not approximately. Perfectly. Every object falls at the same rate, no matter its mass. Why? In Newton's framework, mass has two completely different roles. Gravitational mass controls how strongly an object attracts other objects. Inertial mass determines how difficult it is to change an object's motion. They are conceptually separate properties. And yet, for every material ever tested, for iron, wood, water, stone, they are always exactly proportional, to astonishing accuracy. Why should the property that makes things attract also be the property that resists acceleration? Newton never found an explanation. He accepted it as a remarkable coincidence, one that made the equations work flawlessly. But what if it wasn't a coincidence at all? Einstein approached the problem from a different angle. What if that perfect equality is a clue? A sign pointing toward the true nature of gravity? Consider this. You're sealed inside a room with no windows. No way to look outside. You feel your weight pressing you against the floor. Are you standing on Earth? Or inside a rocket drifting through empty space, accelerating upward at 9.8 meters per second squared? Is there any experiment that can tell you which one it is? Drop an object. It falls to the floor in both situations. Throw a ball sideways. Its path curves in both cases. Step on a scale. The number is identical. No test inside that room can reveal the difference. The two situations are indistinguishable. This idea is called the equivalence principle. If gravity and acceleration are truly impossible to tell apart, then maybe they aren't separate things at all. Maybe standing still in a gravitational field is actually a form of acceleration. That question led to Einstein's breakthrough. Objects in free fall feel no force acting on them. A falling apple, the moon in orbit, satellites circling Earth, astronauts drifting inside a spacecraft. None of them feel pulled. None experience any force at all. They're moving freely, following their natural paths, untouched. But the apple is obviously falling. Or is it? What if the apple isn't accelerating in the usual sense? What if it's moving perfectly straight, and it's space itself that's curved? That was Einstein's radical insight. Gravity is not a force exchange between objects. Gravity is the shape of space and time. Massive objects don't tug on other masses. They reshape the space around them. They bend it. They warp the geometry of space-time itself. The apple isn't being dragged downward. It's following the straightest possible path through curved space-time. Near Earth, space-time curves inward. So the straightest path points toward the planet's center. When you stand on the ground, nothing is pulling you down. You're trying to follow that natural path inward through space-time. But the ground blocks the way. It pushes up on your feet, forcing you off that path. That upward push is what you feel as weight, not gravity pulling you downward. The floor pushing you away from your natural motion through curved space-time. Einstein didn't stop there. He made a bold prediction. If gravity really is curved space-time, then it shouldn't just affect matter. It should affect light as well. Light has no mass. In Newton's universe, gravity shouldn't touch it. But if light follows the straightest paths through space, and space itself is curved, then light must bend. During a total solar eclipse, astronomers looked closely at stars near the sun's edge. They weren't where they were supposed to be. Their apparent positions had shifted. The light from those stars had bent as it passed near the sun, exactly as Einstein had predicted. This effect is called gravitational lensing, and it isn't rare. We observe it constantly across the universe. Massive objects bend the light of more distant galaxies behind them, stretching, warping, and multiplying their images. Clear, direct evidence that space itself curves in the presence of mass. Now think about astronauts in orbit. They float effortlessly. No weight, no up or down. So, zero gravity up there? No. Gravity at the height of the International Space Station is still incredibly strong, about 90% of what you feel on the ground. So why do astronauts float? Because they're falling. The spacecraft is falling. The astronauts inside are falling. Everything is falling toward Earth all the time. The key is speed. They're moving sideways at roughly 17,000 miles per hour. As they fall, Earth's curved surface drops away beneath them. They never hit the ground. They keep missing it. They don't fall into Earth. They fall around it. And because everything falls together at exactly the same rate, there's no sensation of motion, no weight, no pressure, no direction. It feels identical to drifting freely in deep space, far from any planet. This is the equivalence principle in action. Free fall in a gravitational field feels the same as floating freely where gravity doesn't exist. Because, physically, they are the same situation. In free fall, no force acts on you at all. You are following the natural geometry of curved space-time. Think about Earth's surface. It is curved, but when you stand on it, it appears flat. Here's something remarkable. Why is Earth round at all? It's because of gravity, but not in the way you might imagine. It's not that some invisible force pulls everything toward the center, sculpting a sphere. It's that space-time around Earth's mass is curved equally in every direction. Every rock, every drop of water, every particle is trying to move along the straightest possible path through that curved geometry. When all matter follows those curves equally from every direction, the shape that naturally emerges is a sphere. A sphere is the only surface where every point is the same distance from the center. Earth is round because matter moves along curved spacetime. The shape isn't imposed. It emerges from the geometry itself. Even an ant walking what it thinks is a straight line on Earth is actually tracing a curve. From the ant's perspective, It's perfectly straight. That's exactly what happens with everything near Earth. But this curvature isn't just of space. It's space and time together, space-time. Massive objects bend space-time, creating depressions, wells, and distortions. The sun carves a deep well. Earth creates a smaller dip. Even you produce a tiny well, too small to notice, but it exists. Objects moving near these curves naturally follow the geometry, not because something is pulling them, but because they are tracing the straightest possible paths through curved spacetime. The moon orbits Earth because it's following this natural geometry, the curves of space surrounding our planet. That geometry transforms the straightest possible paths into circles. An apple falls because it is following the curves of spacetime near Earth's surface. In this curved geometry, the straightest direction through time points toward the planet's center. When you throw a ball, it arcs in a parabola, not because a mysterious force drags it downward, but because it is tracing a straight path through curved spacetime. And what looks like a curve to you is actually perfectly straight in that geometry. Stand still for a moment. Feel your weight. In Newton's picture, gravity pulls down while the floor pushes up, two forces in balance. In Einstein's picture, there's only one force acting on you, the floor pushing upward. If only one force is present, shouldn't you be accelerating? And you are. Constantly. Your natural path through space-time points toward Earth's center. That's the free fall trajectory. But the floor blocks that path. It pushes against your feet, deflecting you from moving naturally. It's like standing inside a rocket that's accelerating upward. The floor presses against you. Your sensation of weight doesn't come from being pulled down. It comes from being accelerated away from your natural path. The apple in a tree works the same way. The branch pushes it upward. When the branch snaps, that upward force disappears. The apple is suddenly free. Free to follow its natural path through curved spacetime. It falls. But here's the key. The apple isn't accelerating in the Newtonian sense. It is finally moving the way it was always meant to move, naturally. When you stand on the ground, you are constantly being accelerated upward by the floor beneath your feet. Falling is the natural state. Standing still requires a force. That is Einstein's revolution. Once you see gravity as the geometry of space-time, even the most extreme phenomena start to make sense. Take a star, for example. A star is essentially a massive ball of gas. Its mass carves a deep well in space-time. The natural paths through that curved space point inward. So why doesn't it collapse immediately? Pressure from nuclear fusion in the core pushes outward. A balance forms. But when the fuel runs out, the outward pressure fades. The balance breaks. The star begins to collapse. If the star is massive enough, nothing can stop the collapse. Matter compresses to incredible density. Atomic nuclei emerge. Electrons are crushed. What emerges is a neutron star. Nuclear matter compressed to the size of a city. A single teaspoon would weigh billions of tons. For stars even more massive, not even neutron degeneracy pressure can halt the collapse. Space-time curves so intensely that every possible path points inward. Even light cannot escape. This is a black hole. Near it, space-time is warped so severely that light itself, moving along the straightest possible paths, spirals inward and vanishes. We cannot see black holes directly, but we can observe their effects. Matter falling toward a black hole accelerates, heats up, and emits tremendous energy before disappearing. All of this comes from a single idea: mass curves spacetime. Objects follow those curves. From this one principle, everything in the universe unfolds: planetary orbits, tides, the subtle precession of Mercury's perihelion, an effect Newton couldn't explain, but one Einstein predicts perfectly. Gravitational lensing. Black holes. Gravitational waves rippling through space when massive objects collide. The same principle that guides the moon around Earth also shapes the largest structures we can observe. Galaxies. Clusters of galaxies. The universe itself, coherent, elegant, patterned. The behavior of a single small object reflects the geometry of the entire cosmic fabric. Newton's equations still work beautifully for everyday purposes. We use them to launch satellites, calculate orbits, and predict eclipses. They are simpler than Einstein's equations, and for most practical applications, they are accurate enough. But Einstein revealed what gravity truly is. It is not a mysterious force pulling objects across empty space. It is the curvature of space and time itself. Mass tells space how to bend. Curved space tells objects how to move. When you step on a scale, you aren't measuring a downward pull. You are measuring how hard the scale must push to keep you from following your natural path through curved spacetime. When you watch an object fall, you are witnessing it finally free to follow the geometry that mass has sculpted into the fabric of reality. When you look at the moon, you are seeing it trace the straightest possible path through the curved space around Earth. A path that appears circular because space itself is curved. Space guides objects together. That is gravity, not a force, but geometry. And that is far more magnificent than any imaginary pole could ever be.